Hey everyone, welcome to another video. In this recording or in this video, we will be talking about the Raft algorithm. Raft, as many of you must be knowing, is a consensus algorithm. Consensus, in simpler terms, means agreement. So now, there in modern times or in present world, there are many applications that cannot rely on a single server, and because of the load also, and because of reliability also. Most of the applications have multiple servers running behind. Let's say we have uh, data few servers first. We have S1, we have S2, we have S3, we have S4, and we have S5. Let's assume these are database servers. Okay. These databases cannot store different values for a particular thing, right? So let's say we have a value called X, and we know the value of X is 5. We want all of these servers to store the value X is equal to 5. They cannot be storing different values. And this is where consensus algorithm comes into picture to make all of these servers agree with each other on a particular thing. And this one of those consensus algorithm is Raft. So Raft is not the only algorithm that currently exists. There is something called as Paxos. So Paxos existed even before Raft came into picture. There were a couple of problems or issues with Paxos. We'll talk about these briefly in future sections. In this recording, we'll talk about Raft in detail. We'll cover almost every possible scenario and edge cases because these are servers, and at what point any of these server can go down, you can never predict. There can be situation when server 5 went down, server 3 went down. While we still have a majority, we still want our service to be responsive application. So this is where a consensus algorithm helps. So even when you have a few servers which are not operational, your service overall is still working fine. Yeah, and one more thing. So as we talk about the algorithm, the Raft algorithm, we'll also cover the Raft white paper. We'll keep on having a look as well. So this is page one of the paper. This gives an abstract that it is consensus algorithm for managing a replicated log. We'll know what that is. It talks about Paxos because, like I mentioned, it was pre-existent before Raft came into picture. Okay, there are some couple of properties or some novel features that Raft has. It has a strong leader. There is a leader election process, and there is membership changes process. We'll talk about all of these in the upcoming sections. So before we dive into Raft further, there is one small point that you should know. There are a couple of ways in which these servers can be connected with each other. We don't want to talk about all of those in this case, but in case of Raft, there is always one leader present. So we have one leader. This leader talks with all of the other remaining servers, and our client. Say we have a client. This client always communicates with the leader. This is our leader. So this is one small point that I would like you to remember. We'll know why Raft took this decision and why there is one leader and not any other approach as we dive into this deeper. So the Raft paper starts with something called as replicated state machine. What are these? Suppose each server runs a deterministic state machine. Let's say we have, or let me do one thing, copy this diagram. This is one server. This is, you can say, a zoomed in view of one server. Each of these server has a consensus module. You can say the main code, the logic where it executes. The log stores the commands this server has received. The commands are stored in the same order in which they were received. It contains all the history. Then we have the state machine. The state machine actually stores the value of those keys. So we have x equal to 5. The current value of each variable will be stored in the state machine. So x is equal to 5 is stored here. How x became 5? Let's say initially the value of x was 100. We made some operation and made it x is equal to 105. Then we subtracted 100 and made x is equal to 5. So what all logs were there, in what order these statements were executed, and what statements were executed are stored in this log. Okay. Now we want all of this is one server. We want all the servers to process exactly the same commands, the same order, so that all of them stays in sync. To do this, we use replicated log. This thing that I mentioned, this is a replicated log, and the same log is replicated in the same order in all the other servers. There can be situations like a network partition or a node crash, because of which the log for that particular node or maybe multiple node differ. Then at that point, it becomes the responsibility of the consensus algorithm to fix this and make sure all the nodes agree on a particular log. Replicated state machines. So what are replicated state machines? It basically refers to our n number of servers, in our case 5, which replicate exactly the same log in the same order and ultimately have the same state machine. State machine is the final value of all the keys they have. So you can assume it as a key and value pair. So for all the keys, first of all the servers will have the same keys, and all the keys will have the same value in all of the servers. So this is what a replicated state machine is. So a consensus algorithm has some properties. What are those? They ensure safety. So under no scenario, they will return an incorrect value. So let's say there is some failure or any of a node goes down, like I mentioned earlier, it will always return the correct value. And one of the advantages with Raft is it only talks with the leader, and the leader is always right in case of Raft. Why it is right? What are the conditions? We'll talk about this in much more depth as we move along the video. It should always be functional as long as majority of the servers are operational. This is one point we spoke about earlier. They do not depend on timing to ensure the consistency of the logs. So timing means how much delay of or how much time it takes for a message to replicate in all the machines. It does not talk about the time at which a log entered. In a common case, a command can complete as soon as a majority of the cluster has responded to a single round of remote procedure calls. So Raft uses RPC to communicate with all of the servers. So we had 5 servers, right? So Raft uses RPC amongst these servers to communicate with each other. So this point says as long as majority of the servers have received the RPC, the Raft can proceed with the next step. It does not wait for all the servers to respond back, because there can be a few servers which are slow. As long as the command is acknowledged and has been processed by the majority, it is good to go. So what was wrong with Paxos? To give an overall gist about this section, it was very complicated. Most of the population, and the population which I'm referring to are research scholars, they were not able to comprehend how the algorithm is actually working. Even after being explained, they were failing or not able to answer the quizzes about the algorithm very clearly. And this was the problem that was faced by the Raft creators as well. And that was the reason they thought of creating a new algorithm which is easy for the mass public to understand. And that's what the next section, designing for understandability, talks about. Oh, here it says, but our most important goal and most difficult challenge was understandability. They wanted to make Raft easy to understand for a large audience. In order to make it understandable, what did they do? They followed two approaches. Here we recognize that there is a high degree of subjectivity in such analysis. We use two techniques that are generally applicable. The first technique is the well-known approach of problem decomposition. So they broke the consensus into separate parts. So the whole process of achieving and maintaining a consensus has several steps. So they broke those steps down into three smaller steps that can be managed independently and explained independently. We separated leader election, log replication, safety, and membership changes. So the Raft, instead of focusing on solving all the problems together, they separated these problems into separate phases, and we can look on each phases independently. And in a bigger picture, all these phases or all these steps work together to make Raft secure and highly reliable. This was the first technique, that is decomposition. The second approach was to simplify the state space by reducing the number of states to consider. What does this mean? The more state you have, the more values you have to manage and more calculation you have to do, right? As the number of states increase, it becomes, what do you say, complicated and difficult, and at times confusing also to manage those. The Raft tried to reduce and keep the number of states as minimal as possible. The logs are not allowed to have holes, and Raft limits the ways in which logs can become inconsistent with each other. Again, we'll know how the Raft ensures that as we move forward, but this is the ideology or the technique which it followed. Raft mainly focuses on non-determinism, but there is one thing where it wants to be non-deterministic, and that is leader election. It did not want to add another state to maintain who was the last elected leader so that the same leader is not elected again. Here they chose non-determinism, that is randomization. They don't care who is elected, which server is selected as the leader, as long as they follow some certain rules. I mean, the server follows certain rules. So randomized approaches introduce non-determinism because if something is random, you cannot determine the value, right? But they tend to reduce the state by handling all possible choices in a similar fashion. Choose any, it doesn't matter. So in case of Raft leader election, they chose to go with randomization simply because it was easier and it doesn't make any difference who actually is the leader. Okay, so now let's talk about the Raft consensus algorithm. We discussed earlier that Raft has one leader, and this leader only is used to communicate with the client, and this client does not connect with any of the other servers. In case the client connect, let's say with S1, S1 returns that no, I cannot respond to you. So it's better to talk with the leader, and S1 will tell how you can reach out to the leader. The client will initiate another connection that will connect it to the leader of that term, that is S2. So why did Raft choose this method or implement it this way? Simple answer. It makes things easier. So if you read this, Raft implements consensus by first electing a distinguished leader, then giving the leader complete responsibility for managing the replicated log. The leader accepts log entries from clients, replicates them on other servers, and tells servers when it is safe to apply log entries to their state machine. Let's understand this first. Okay. Now let's again draw a couple of servers. Let's assume for now, this time S5 is our leader. Okay. And here we have a client. This is our client. Now remember, each of these servers has a state machine and a log, correct? Now let's assume this is a brand new state and currently there is no data. Okay. What we'll do, so the client will connect with the leader and let's say it says store x is equal to 10, y is equal to 5. Okay. Now what this will do? The leader has state machine, right? The leader has a state machine, the core algorithm, and a log. So what the leader does is first of all, it in its log. So let's say this is our log, this is our log, and this is state machine. So it won't go and change anything in the state machine immediately. It will first store these values in the log and it will tell all the other servers parallelly that I have received something, you also do it. So the other servers, they will store in their log the same values, x is equal to 10, y is equal to 5, x is equal to 10, y is equal to 5, and so on. Similarly for S2 and similarly for S1. None of the servers has the value stored in the state machine as of now. So all these values are replicated in the log, right? Why does it happen this way? This is, you can say, a safety protocol which ensures that only when the log has been replicated to majority of servers, only after that the value will be committed and stored in the state machine. So this value gets committed to the state machine. So x is equal to 10 and y is equal to 5 is stored first of all in the leader's state machine. Then the leader calls another RPC and tells the other nodes to commit it and store it in their respective state machines. So this is how the value is replicated. Now, if we go back to the statement, the leader accepts log entries from the clients that we did, replicates them on other servers. So here we saw the replication and tells servers when it is safe to apply log entries to their state machines. It is safe when majority of servers have copy of that log. Having a leader simplifies the management of replicated log. For example, the leader can decide where to place new entries in the log without consulting other servers. So this makes the process simpler. Let's say if there was no leader and the client could connect to any of these nodes. Now this node has to first of all form a consensus or see what is the current state, because you never know if this node itself is not updated. But in case of Raft, the leader is always going to be the most updated and the most updated node with 100% correct values. So having one node with that responsibility simplifies the process. And this is why this mechanism was chosen. Okay. Given the leader approach, Raft decomposes the consensus problem into three independently subproblems: leader election, log replication, we'll talk about this, and safety. If any server has applied a particular log entry into a state machine, then no other server may apply a different command for the same log index. So all the logs, this says that all the logs should always be same. Let's say this was log entry 1. Let's say another command from the client was do x plus 5 and do y minus 5. So when this comes, again the leader will handle it. Leader will add it first of all in its log entry, then it will try to replicate this log in other servers. So at no scenario it is possible. So this was index 1, this is index 2, this is index 1, this is index 2. Under no scenario it is possible that these two indexes have different command. If this is x plus 5 and y minus 5, this also has to be x plus 5 and y minus 5. So all this, so you can say these are the conditions or these are the rules. How these rules are enforced will know again as we dive deeper. Okay, this was log replication. Right. Now, as we have discussed earlier that Raft uses RPC for communication. So this is how the RPCs look like. So there is append entries RPC, there is request vote RPC, rules for servers, a couple of rules for servers. We don't have to look at this immediately. We'll see if we have some time left in the end. Uh, because anyways, we'll cover all this in the following sections. Cool. So Raft guarantees that each of these properties is true at all the times. What are these properties? Election safety. At one point, there can be only one leader. It is leader append only. A leader never overrides or deletes entries in its log. It only appends new entries. So you cannot go ahead and update any previous value. That is not possible in case of Raft. If you have to update any previous value, have to add that in a new log, and this new log will always come from the client. A server cannot create an own log and then tell other servers to update it. That is not possible. Log matching says if two logs contains an entry with the same index and term, then the logs are identical in all entries. There is a word term that is showing up repeatedly. Let's understand what term is. You can associate term as a normal election term. Let's say in a country, election happened in 2010. The very first elections happened in 2010. And let's say it was an election is valid, a leader is valid for 5 years, and the election is conducted again in 2015, 2020, and 2025. Right? So this is term 1, this is term 2, this is 3, and this is 4. So similar is the case here. So now this is the very first term, assuming, and this was term 1 of this election. Okay, there can be scenarios that the leader the leader node went down. The server was no longer responsive. Then what will happen? These four nodes will try to become leader, and there can be only one leader at a time, like we discussed. That is a rule. So an election will start again. One of the nodes will become leader, and another term will start. This will be called as T2. So what is it saying? If Yeah, if two log contains an entry with the same index and term, then the logs are identical in all entries up through the given index. So let me show what this means. Yeah. So this was term one, index one. This was term one, index two. Now let's say the node crashes at this point. Another term is started. This is term two, index one. This is term two, index two. So that point says for all the entries, this will always be the same. This is T2 index 1, this is T2 index 2. This history, let's say we are comparing at this point, all the indexes before this will be exactly same in all the machines. There won't be any difference. There is no possibility of any difference. When there is any difference, there are mechanisms in which that difference is rectified. And how those differences can happen, we'll see. So currently, this is all giving an overall view. Deeper depth, the deeper diving of all these topics will come in. Leader completeness, if a log entry is committed in a given term, then that entry will be present in the logs of the leaders for all higher numbered terms. We can skip this for now. This can get confusing. And a state machine safety says if a server has applied a log entry at a given index to its state machine, no other server will ever apply a different log entry for the same index. So this means that if at this point at T2 index 2, after this log was replicated in all of the servers, something was applied to the state machine, all the other machines will always apply the last log or that log in their state machines. They cannot apply any different log. It's not like, let's say T2 said x is equal to 10 and T2 index 2 said x equal to 10 and T2 index 1 said x is equal to 7. It's not possible that when the leader sent apply command, not like any server can, apply any older log. It has to apply the latest one only. Okay, so Raft has three states. There is all over, there is candidate, and there is a leader. Okay, these are the three states in which each of the server belongs to one of these states. So let's say you spin up a new server. Server has three nodes. It is brand new. Okay, these servers, there is no leader currently. So how do, first of all, you might question how do the nodes know whether there is a leader or not? When there is a leader, the leader keeps on sending heartbeats to the rest of the servers that, okay, I am there, I am alive, I am functional. When the servers stop receiving this heartbeat, they know that something has happened to the leader and it's time to conduct a new election. So this is how they know. Okay, let me remove this. Okay, so now we are starting up a new server and we currently have three servers. So when this comes into, so initially all of these servers, they start with a follower state because they don't know, they are not the leaders and they are not the candidates. So candidate is someone who wants to stand in an election so that they can be elected. Initially, all the nodes are in the follower state. When these nodes don't receive any communication, they know there is no leader or something has happened to the leader. So what they do, they shift to the candidate state that they want to participate in the election. As soon as they shift in the candidate state, what they do two things. They vote for themselves because obviously everyone wants to be the leader. They will vote for themselves. So vote for them. They will vote for themselves. This first thing will do, and they will request vote. There's something called as request RPC, request vote RPC. There is request vote RPC. Let's say S1. S1 was the first candidate, was the first node to shift to a candidate state. It will vote for himself, so it has one vote, and it will request S2 and S3 to vote for it. Make me the leader. Request. It will request for votes. So S2 and S2 can decide whether it wants to vote S1 or not. It's not like it has an opinion. It will There are some couple of rules which S2 will check. If S1 satisfies those rules, S2 will vote for it. Similarly, S3. But if those rules are not satisfied, S2 can reject the request that no, I don't want to vote because you are not meeting the criteria. Similarly, S2 can also shift to the candidate state and S2 will vote for itself. Let me change the color. Yeah. S2 will vote for itself. S2 will try to request votes from these two. Now, S1 will also check whether uh, those conditions are satisfied here or not, right? So, and at one time in a given election, one node can vote for only one node. It's not like one voted for S2 also and S3 also. That is not possible. In a given term, we discuss what a term is here, right? So this election happened only once here, right? Election happened only once here, and one person can vote only once. The same is the case here. So when let's say S1, S2 also requested and S3 also requested for a vote. If S1 has already voted S2, S1 will reject the request for S3. I hope the point is clear. So yeah, so these are the three states. Server starts up with the follower state. When there is no heartbeat from the leader, it will start an election and it will move to the candidate state. So the candidate, first of all, will vote for itself and it will request other servers to vote. Once it has received the votes from majority of the servers, it will become a leader. Okay. Now there you can see the discover server with higher term, discovers current leader or new term. So these are more scenarios. We'll talk about this in the next part of this series. So stay tuned.